So good morning, everyone. It's week 8. Yay. Okay, so this timing is pretty interesting, kind of nice, I think, because it's week 8. Next week is Thanksgiving, and then you only have one more week, and then finals week. So that's pretty good. So I feel like I've been saying this all quarter, but today we're gonna have to go really fast because we gotta do lots of stuff today. We're gonna cover 2 chapters in one day, but I have a very special announcement, so bear with me, and maybe you know what it is, but I think it's good. So hide meeting controls. Okay, so today we're doing differentiation and integration. Of course, we're doing this on MATLAB. So with MATLAB, it's basically quite nice because there's numerical methods, but the code is not too bad in my opinion. So we're gonna try to go through this, do some examples, and thank you very, very much for the Wednesday class joining today. I appreciate your understanding and being flexible with my time. So I promise the lab won't be difficult today, but we do have a lot to cover. So let's get started quickly. So who got started with this warm up? Yeah. So, okay, the derivative of the first one. Okay. All right, you got that? Okay, integral. Oh, second derivative, did I ask you that? Yeah, second derivative, 6x, good. Integral. Good. Remember the plus C? Get all the points. Remember, you need to get all the points. So in your math class, you need the plus C. In this class, let's see what the equivalent of that is. Maybe it's like fixing your bugs. Just make sure you get all the points. Did anyone try this one? Yeah? So what do? Okay, good. So the derivative, the velocity is the derivative of the position vector. So what's the derivative of cosine cubed x? Okay, and then the second. Okay, very good. So we're taking the derivative. Keep in mind, we're not going to be focusing on analytical methods today. We're focusing on numerical, but just as a reminder, the derivative is an operator and it acts on this vector. Okay. So if you don't quite remember that, it's not super important, but I think it's a good primer for today's lecture. So -3 sine t cosine squared. If I ask you for the acceleration, what would you do? Take the derivative again. It'd get pretty messy at that point. You got chain rule, product rule, and then so for the speed, how would you take that? Say it again. Not the absolute value quite. It's the same notation, but don't get confused with the absolute value. It's going to be the magnitude. So remember, way back in the beginning of the quarter, we learned how to take the magnitude of vectors. So it's just like the Pythagorean theorem, applying the Pythagorean theorem in R2. Okay, so this is the magnitude of the vector. So therefore, the speed. If velocity is a vector and speed is a scalar, just like way back a million years ago at this point, right? So I think I'm recording, right? I was recording. Okay, cool. Great. Thanks a lot for your patience again. Now let's truly get started. Like I said, we're going all the way back. I showed this on day 1. Lecture 1. So we've done all these, we've pretty much done all of these. Did anyone go back to do inverse and transpose? Any chance? Shucks. I was hoping y'all went to read. I was in chapter 4, I think. But I encourage you to do it anyway, because you're gonna need it for sure for your senior year. So today we're doing single variable calculus. And then this is going to pretty much wrap up the entire class. We're going to do DEs in the final week very quickly, but pretty much this is it, y'all. This is pretty much, look at that. Chapters 1 through 9 in 8 weeks. So like I said, we did, like I said in the beginning of the quarter, we're doing approximately 1 chapter a week. And so we skipped eigenvalues, we skipped Fourier. I think I mentioned this before. I didn't learn these in undergrad either, but I learned them. I got introduced to them in grad school. They're really fascinating methods, and they have applications in all types of engineering. So we're doing differentiation and integration today. We're doing it on MATLAB. Typically, we're going to start with derivatives and then do integrals. But for the sake of time, let's just do integrals today, and then if we have time, we'll do derivatives. For derivatives, we're going to try to do at least finite difference approximation. So that's going to be the most useful. And then you can also derive the equations using Taylor series, Lagrange polynomials, and then differentiation using curve fitting. So really, we're combining all the lectures down to one single objective, which is to calculate derivatives. Okay. And then for chapter 9, if we can get to, we're going to do an example on Simpson's methods. Okay. And then I encourage you to check out Gauss quadrature. So if you're going to get tested, let's say on your quiz, my guess would be it'd be one of these two. So make sure you study these two. This is my guess now. This is my recommendation. That's not going to show. Okay, so make sure you study those two. So we're going to cover Simpson's methods today. And so the derivative gives you what? Versus the integral gives you what? Don't be shy. Good, good. Anyone have anything else to add? Pretty much agree? Okay. So like I said, we can start with integration. So integration, of course, gives us the area under the function. So if we have some function f of x, we can approximate it. We can get the exact calculation using the analytical integration, and then we're going to learn how to approximate them using different methods. So like I said, I'm going to take time to do this, to do the integral examples. So we can, I don't like the way that the book did the examples this chapter. So we're going to try our own, hold on, I'm going to stop share for a second. We're going to try our own examples. Okay. Share screen. Close. Week 8. Friday. What are you doing? We're gonna have to use this. I don't know what's doing that. Okay, all right. So the question reads, calculate the integral of f of x squared. So let's do it from like what, 0 to 4. So someone go ahead and calculate that integral analytically, and then we're gonna do it numerically. So calculate the integral of f of x equals x squared dx from 0 to 4, right? So you can just give me the fractional value. So let's say I analytical would be what? Okay, let's say if a equals 0 and b equals 4, then I would just simply type b cubed over 3, right? Minus a cubed over 3. Do you agree with that? So you got, say again, 64 over 3. So we can do I check. So if these two are the same, then we agree with each other. Not there's an issue. Okay, so we agree analytically. But of course, we're trying to do this numerically. So remember how back in the day we tried to plot stuff so we can visualize it. So how do we plot functions? Don't be shy, you can plot it yourselves. So try and plot the function. Get out your MATLAB. So now we know several ways of plotting stuff now. So I'm going to go ahead and just make a vector from x equals. Okay, so I want to define like a delta x. Let's call the delta x our h. My h is going to be my delta x. So that's my increments. So let's say that's 0. Let's make it large at first, 0.1. And so my x, I'm building a vector from where to where? Yeah, from A to B, right? From A to B, and then I'm going to calculate my vector, x squared, and then plot that. X comma f of x. Pretty much check that. Okay, so do we kind of agree? That's what x squared looks like from 0 to 4. So we're trying to calculate the area under this curve, right? And we already know what the answer is going to be. But so here's a trick. Before we get into the methods, I want to give y'all a trick because this can be useful for your labs. So we're going to apply the Riemann. We're going to apply the concept of Riemann summation. So how do we? Well, there it is. So here's our function. And then who can tell me what is the concept of Riemann summation? What are these? Yeah, exactly. So the rectangle, what's the area of a rectangle? Yeah, it's just your base times height. So let's say, okay, I'm gonna test y'all, see if we're awake. So what is that length? So if we have, this is x, let's start with this one. If x1 is a and x2 is x2, what would be that length? It's going to be x2 minus x1, right? And then, so that's your delta x, and then your delta y is what? Yeah, so it'll be f of x1, this one. This is your y. So therefore, the area is length times width, right? So that's going to be the first rectangle, let's say I1 is going to be that delta x. So we're going to call delta x h because that's constant. And then it'll be f at x equals, where's x? x1. Good. So then we do that over and over and over again. And then, as you may presume, we could do vectors, we can do for loops. With the composite rectangle method, we're just going to be needing vectors, basically, right? So I'm going to say h, that's my thickness here. This is my thickness of the rectangle. So all I need to do is calculate what? I need to calculate a new vector. Call it the areas. The area is going to be what? So what do I plug in with this equation? Basically this equation, right? This equation. So my h is a constant. My h is a scalar value. So I'm just going to say my h times my f of x. Basically, that's it, right? So my area now will be another, what type of mathematical object? Area, what is that? So if I have a scalar, what is f of x? It's the function in MATLAB. What is it in MATLAB? Yeah, vector, good. So therefore area has to be a, good. So now the area is going to give me the area of each of those little tiny rectangles at each point, right? So is this my integral? What's my integral then? Yeah. So I can say the integral is going to be the sum of a. So I'm going to suppress everything except for, let's see, this will be I check, this will be I analytical. And then we can call this like I numerical, right? So do I expect the values to be all the same? No. So this one, the last one is what? It's an approximation, right? So how do we get that answer closer together? Yeah, we can make the thickness really small. We can add more rectangles. As we take the limit, as h approaches infinity, we approach the true answer. So we can't get the true answer, but we can approach the true value numerically. Pretty good. 0.1% error. Or less than 1%, like 5.5%. Okay. So this is like the, this doesn't have to do with the chapter, unfortunately. So the chapter is now we got to learn these methods. That was kind of like my little, that's my cheat codes. That's what you do in your projects. Today, we want to learn these methods so we can get better approximations quickly. And these are going to be basically useful if you have very large computational sets of data. So these are the methods that like your software uses. But if you just want like something quick for your labs, what we just did is more than fine. So Simpson's formula, we like to go through the derivations, but we don't have time. So where do y'all suppose this comes from? Newton's. Before I interchange I'm going to have to get back where this actually comes from. I want to say this is from the Taylor series. Do you all agree with that? I'm going to have to verify that because it's a very long derivation. But the point is, we're going to use this formula. So we have h over 3. So therefore, this is called the Simpson's 1/3 formula. So we have, so what is that guy? So we have f of a. So where's f of a? Yeah, the initial one right there. And we have f of b. Where's that one? The final one. Okay, so we have these funny summations. So the summations, first of all, I dislike the notation. It's saying I equals 246. All that's saying is just add by 2. So we're counting the even ones. And then this one is saying also add by 2. So we're counting the odd ones. And so, for instance, this would be f of what? Xi starts at I equals 2. And we would add, let's circle these ones. So if I want the summation of this one, which one would we get? So what's our first I? Where do we initialize? I equals 1. I equals 2. Good. We already started I equals 1 with f of a. So we're going to start I equals 2. Good. Next. Let's stick with I. I is 4. I is 4. So f of xi is, which one do I circle now? Two, add 2, 2, 4. Okay. Then the next one would be 6. And then 8, 10, 12. So this is your even. This is your even ones. This is even. And then this is odd. Odd. Okay. So we have some scalars here. We're going to multiply by 4. We're going to multiply by 2. Okay. Any questions about that? So let's see how much time we have. Let's program this. We got good time. We can program this. So we're going to do I numerical. Now let's try calculating using Simpson's 1/3. So I already have my A, my B, and my H, right? These are the main key parts. So I'm gonna give y'all a few minutes to, I'll give you 5 minutes to try to program that, actually. I'll give you all 3 minutes. Really, this is just me buying time to make sure I have the right answer. Chapter 9. So remember, we're trying to integrate, what's our function? X squared from 0 to 4. Right? X squared from 0 to 4. Okay, so I'm sure y'all are aware by now. And I know that I asked this a lot, but remind me one more time, raise your hand if you are a transfer student. Can you put it higher real quick? Okay, and then everyone else, raise your hand. Y'all started freshman year and then y'all already took some engineering classes. So even though we all started at different starting points, I'm hoping by now you realize that the math is important, and within this major, we use the math to solve the problems. So all we have to do is translate this math. We got to just apply it. Okay. Did anyone proceed? So how would we program that? So we already have our A, right? We already have our A. We have our B, okay? So why don't we start with the summations? So how do we do that? Okay, for loop. So for I equals what? Where do we start? We're going to start with only this one. So we're trying to translate this equation into code. That's what we do as engineers. So I equals 2. Oh, oops. I equals 2. And then we can skip by 2, right? So in your C++, you got to do something like, I don't remember, I++ and then add by 1. So we add by 2, and then we're going to stop at, where do we stop? We're going to have to define n as the length of x, right? Okay. And I'm going to give you another equation. I think y'all can handle it. Instead of guessing the thickness, we're just going to actually define the length. So careful with the code. You know, if you just copy straight up, it might break now. So I'm going to say the h, how many rectangles do we want? Let's define that. 1,000? Let's do 1,000 rectangles. Let's keep it simple. Let's start with 10 rectangles. We're going to say h is, so what's a good equation for h? So remember, h is my thickness. This is my thickness. So what's a good equation for h? Yeah, b minus a over n. So do we kind of remember this from the calculus from all the way back? Or maybe not so all the way back, maybe this year. We go from our b minus a, and then if we have that increment, we want to divide it by n rectangles. That's all we're doing. Okay. So that's that. And then, so that's our h. So we have our n is going to go up to 10. So we have to be careful with this. Check out these conditions. Remember, before we do the code, we need to see the conditions. So the interval must be equally spaced, which we're doing from the definition. And the number of subintervals must be an even number. So did we satisfy those conditions? Did someone say no? Is it not? Because n is 10? Say it again. We can fix n equals 10 by defining it. So make sure n is an even number. Make sure this is even. This is my thickness. So we can fix n equals 10, and now we have our for loop is ready to go. So we're counting from 2, 2, 4, 6, 8, stop at 10. Now we're just going to define this summation. Let's call this area even. That's our even summation, right? And that's going to be sum of, no, let's just call it the f of xi. Okay. Let's run if our code works. Any questions about this? So we calculated this guy. We calculated each of those function values. So A even is a vector, right? Apparently not. F even at I. This is the key part. We have to do the F even at I. Okay. So A even should be a vector. Okay. And then we're going to want to calculate the sum of all that. Now we're going to do the second summation. So now we're doing for, we're out of this for loop. So we can just use I again, but let's just use J now, just in case. I'll get confused. So now where does J start? We just simply read the equation. J starts at Y1. 3. We're starting at 3, we're incrementing by 2, and then we're ending at 11, 9. I'm just going to say n minus 1. But that's correct. N minus 1 is in fact 9 because n equals 10. So now this guy is going to be a, let's call it odd of I, another vector. This is where my bug was last night. We need to call this J. Odd of J, and that's just going to be f of x of J. So all I'm telling MATLAB is, hey, I want that part of the vector. Just give me all the odd parts. Now the final step is the answer. So let's call this I 1/3. So we're applying this equation. What's that equation? Do we know H? We have H over 3. Point times, because we're doing a vector. So f of A, I'm going to say, what? F of, sorry. Okay, thank you. Fx, thank you for that. So I want that first index. So I want f of x equals 1. Let's start to cross this off. No, I can't. Okay, the first one plus 4 times. So do we have this? We need to take the sum of that, which was this one, right? So that's my sum of my A even. Plus 2 times, we have that one, right? And again, we take the sum of my A odd. And then finally, what's the last one? F of B. Oh, look, we can say F of, no, we're gonna have to say F of 1. Yeah, F of 1. And then this should be F of, so this is B, but in MATLAB, we want the last one, which is gonna be, should be the last one. So it should be N, if I'm not mistaken, right? So if you don't like this code, there's many ways of doing it, but I think it's way better than the book. I don't know what the book was doing this chapter. Pretty good, right? We did 4 different integral calculations. Let's see if we can get these to converge. Let's see if we can get these to converge. So how do we do that? Let's make many rectangles. Let's try 10 to the 4th. And remember, if your code is on an infinite loop, what do you press? On Mac, I don't know, I forgot. On PC, I think it's Control C. Okay, look, great. We did the analytical way. We checked it. We did the vector numerical way, and we did Simpson's 1/3. And they all seem to make sense numerically. Now, does someone have any questions about what we did with the math? So all I can tell you is my tip is just like before, you have some method. It's going to ask you, all right, use this method. You go into the book, you read the equation. Here's the equation, convert the math into code. That's pretty much it. All right, any questions? It's Control C on Mac as well. Thank you, Sam. Great, great. Okay, the rest of it, I think y'all will be fine without an example on differentiation. But again, you just apply whatever the equation is. So the true derivative of a function approaches, the limit of the delta y over delta x as the difference approaches 0, approaches the true value of the derivative. Okay. And basically we have three most important methods: the forward finite, backwards finite, and central finite approximation of the derivative. So this is just really quick. Just use these equations. You'll need this for your labs, for your homework. Basically, we're just getting the xi plus 1 or the xi minus 1, or just the difference between those two. Okay, any questions about that? All right. I think we don't have time to go through this example, but I think y'all will be fine for the derivatives. I think the integral one's a little bit trickier. The derivative, just apply the equations. These numerical methods can get really lengthy. These ones, I'm confident that these are from Taylor series. So if you expand the Taylor series for the first derivative, you're gonna get these formula. So again, these might be useful for your projects, for your classes, but pretty much we're gonna focus on the 2 and 3 point forward and central. So I think you're gonna need this one and maybe this one. So try to study these. They're just the equations. And then if you have time, I encourage you to look at the derivations as usual. Questions? Okay, so that's pretty much it. I'm just gonna I'm gonna stop recording. The rest of this is just class housekeeping.